Okay, so now in this additional example here allowed me to show how to use the washer's method here into finding the volume of a solid that is generated by rotating a region around a given axis. Okay, so let's now turn over to our wording description of the problem right here. And of course, before we proceed right here, it's needless to say this particular video lesson here must be viewed after you have seen my complete lecture or the general lecture on the washer's method right there. Okay, so here's the description of our problem right here. So we want to find the volume formed by or generated by rotating around or about the x-axis, the region that enclosed by x equals 2y and y squared equals x right here. So let's get to know about our region first. So we have a region that that is, the wording here says enclosed by, and there are two given curves. So x equals 2y, so this equation here gives me a curve, gives me a graph. And there's another equation here waiting for us, y squared equals x right here. Okay, so now on the computer screen right here, allow me to quickly switch over to the computer screen right here. Okay, so these are the two curves that enclose our region right here. So let's find out what that enclosed region looks like before we put into our imagination the next step, that's we're rotating the enclosed region around the x-axis. Okay, so now on my browser, okay, with the empty graphing space here, all right, so the curve x equals 2y. These are the curves here. All right, so this straight line right here is the graph of that equation x equals 2y. All right, and then this sideways parabola right here is the graph of the curve y squared equals x. Okay, so this y squared equals x right here is the one that is the graph. Is this equation y squared equals x is the one that has the graph being the sideways parabola, whereas this straight line right here is the one that is having equation x equals 2y. Okay, so now the region is supposed to be the enclosed region. That means so definitely we have to imagine where our region is. So the region cannot be out here, it cannot be here, it has to be that region where my mouse is right now pointing at. It's that region enclosed inside of the being trapped inside the two curves here together. All right, so now let me put the shading of the region on so that it's more easily recognized right there. All right, so here we go, that's our region, and now I am going to restrict the curves to only show the region, the bounded region here. So now that's how the curves, that's how the bounded region look. All right, and so now in 3D view, so the idea now is that back in the problem with that given region, we are now going to rotate that around about the x-axis. All right, so that's the key right there, about the x-axis. So let's now look at our picture over here and imagine that what's going to be the solid, what will the solid look like when we're rotating this region about the x-axis. So the x-axis is right here. Okay, so the problem chose for us to rotate this region around the x-axis. So in that way we will have a solid, but let's find out what the solid looks like, and then we're gonna come up with a plan to calculate the volume of that solid. All right, so now this is in 3D view, the x-axis is coming out this way, this is the y-axis as usual, and I'm putting in the perspective right here, and this nice graphic right here is created with decimals. And this is the third axis for the three-dimensional system right here. All right, and so as I have explained in my general discussion video lecture about those volume methods, either the disk method or the washer method, then rotation orientation does not matter. So here I'm rotating clockwise. All right, so let's observe now. Okay, so here's how it looks. So right about halfway of the rotation, and that's what the picture looks like. So the real solid volume is this part right here where I'm pointing at. Okay, but the green space right here is supposedly the empty space. Okay, and so now I'm going to complete with that. I'm going to go ahead and complete with that rotation right here, and that's how we create. So we have a solid where it looks like a cup outside, but inside of that there's like an empty cone being put inside of that. Okay, and so maybe viewing it with a halfway rotation would reveal the story a little better right there. All right, so now in that case right there, let's now turn over to the board and let's draw the picture right there, the description of the picture. And from that picture, we are going to come up with a plan of how to solve that. All right, so from what I saw with Desmos, okay, so here's the x-axis, and here's the y-axis. Our curve, we have a region that looks like that. So this bent curve right here is y squared equals x, and then this other curve is there's another straight line curve right here. Okay, and it looks like the two curves crossing each other. And so this one curve here at the bottom is x equals 2y. Okay, so we have two curves like that. And so the shaded area is inside here as described by the picture. And so now if we're rotating that region around the x-axis, and we have seen that on the Desmos already. So now I'm going to actually just put in the stripe. So just like how we have learned that idea through the general discussion video lecture, then now we know for sure that we have to draw the stripes in our region. We have to place a stripe in our region, but the stripe is going to have to go through the region and reach to the rotation center or the rotation axis in a way that any stripe through the region must be perpendicular to the rotation axis. So we have our rotation axis here. All right, so that's our rotation axis. Doesn't matter what orientation we go with that rotation. Okay, and we place our eyes according to the multiple times that I have already explained. Then we're placing the eyes to look right into the rotation axis. So the x-axis is coming this way, and my eye is looking straight at it. Okay, and so now again back to the stripe that I'm currently drawing. Then we need to leave. I'm going to leave that dotted line right here. There's some part of that stripe being dotted line just to indicate that some part of that stripe is outside of the region right there. So it's the way it is, and that's what makes it unlike the disk method right here. So when we're about to construct it, when we're about to rotate right here, then some part of the stripe here stays outside of the region. Or another way of saying, the stripe here, in order for the stripe to reach to the rotation axis, the stripe must cross through the boundary at some point, at a point right there. Okay, and so, or at least at one point. And so now in that way, when I'm rotating, okay, here's the picture right here in front of our eyes right here. We're gonna have now there's always and that crossing point where the stripe is crossing through the boundary, it's creating a point where it's closer to there's always a point closer to the rotation axis versus a point on the other boundary that's further away from the rotation axis. And so that's why we have now once rotated, we're going to have an inner circle due to the point that's closer to the rotation axis, and then we have an outer circle. All right, and so together what we have here is a washer. Okay, so in front of us here, what we have here is a washer, and that's why we're calling this is the washer method right here. Okay, and so as a complete picture, then once we rotate it, then this solid is going to go through just like that. Okay, and gives us, okay, so that's how I'm seeing the rotation. All right, that's how I'm seeing it. And so now with a further imagination, the washer is going to look as following. This is where our x-axis is, and so we have inner circle and outer circle right here, each one of those. Okay, and that's the idea. And then for each of the washer here, we have a thickness. Okay, we have a thickness. All right, and then as we're looking at as we're placing our eyes to look straight at each of the washer here, each of the cross section of as being a washer, then we're looking at two concentric circles. as I have explained in my general discussion lecture about this method. All right, so the concentric circle here, the outer radius, or the larger the radius gives me the outer circle, and the inner circle here, the smaller circle here, is created by that smaller radius. Okay, so this is the washer, the solid washer part here that we are seeing, and empty spaces in the middle. Okay, so solid washer part is here. All right, and then empty spaces in here. Okay, with a thickness. All right, so now in that way, we have turned that into multiple different views like that for us to see our, and this is the reason why, again, this method where we're going to be accumulating those volumes, it's the washer method right here. But in the end, one fundamental that exists throughout the entire lecture there when I was doing this, calculating volume of a solid generated by a rotation right here, then we always, at any stripe right here, once rotated, we create a cross section. Okay, and now all we need to do is to find the cross section area. Okay, that's only one fundamental, and then we're going to multiply that cross section area with the thickness, and the picture of the thickness is described right here. Any washer has a thickness. Any stripe that we're drawing has a thickness. It could be infinitesimally small or thin thickness, but we have a thickness. And so multiplying the cross-section area, now the cross-section appears to be a washer. So cross-section area multiplied with thickness will give us the volume of one infinitesimally thin washer. Okay, and then with that volume, now we're going to be accumulating all washer volumes from a start. Okay, and we will discuss about the start and the end of this accumulation later. But we're going to have from a start to an end of that accumulation, and that's how we are going to find our total volume right there. All right, so now again, I am going to let's start looking at allow me to erase this picture, and I will redraw that somewhere else, okay, in a different space of the board. But so in a way how we're placing the x-axis is here, in a way how we're placing each of our washers, then the thickness here has to be, or must be, the infinitesimally small change in the x values right here, or that's dx. And so now, just to be consistent with the steps I pointed out in my general discussion lecture, in my personal experience, finding the thickness is the easiest. So now thickness of each of our washer here, just in how I just now explained, then the thickness is realized to be dx. All right. And then once the thickness is realized to be dx right here, then we immediately can revise our integral. So the cross-section area, we haven't found that yet. Let's leave it there for now. Okay, cross-section area. All right, but then the thickness now is dx. All right, so we have a thickness now being dx, and this dx now will become our differential d expression inside of our the integral problem, and that will consequently lead to the next step, so that we should derive our cross-section area here as a function of x, okay, because the d expression here is now in terms of x. Okay, so now let's start looking for our cross-section area. All right, so cross-section area. Okay, and so now I am going to erase this picture, or actually I am going to move out to my other board right there. Okay, so again, I drew that picture earlier, and I had to sadly erase that. But if we placing our eyes to look straight at that, where the x-axis is coming out this way, then there's at any washer we will have an inner circle and an outer circle. Okay, and so inner circle comes out from a smaller radius. Okay, and then outer circle comes out from the larger radius. So there's a larger radius, big R, and smaller radius, lowercase letter r right here. But the area of any washers like that right in front of us, just the area of that current cross-section. Now notice again, empty space is right in the middle here. Okay, so the real space the real amount of area we're calculating is here in the part where I'm shading it. So that means the total area there has to be pi times bigger R square, because that's the area of the larger the circle, and then we're going to subtract out the area of the smaller circle, which is pi times little r square. That's the general formulation of this, of any of these washers cross surface. Okay, and so now back into the actual picture. Then in that way, larger area, larger radius is this much amount, okay, of height right here. So when we're placing our stripes to be perpendicular with the x-axis here, then each one of our radius is going to be the height that comes out from where the x-axis is out to the function on each one of these curves. So each one of these curves now has to be expressed as a function of x. Okay, so how about larger radius? The larger radius, see right here in this picture in red ink right here, the larger radius is from where the center of rotation or the axis of rotation out to the further curve. See, out to the further curve. I'm using that term right here. So from the rotation center, this curve right here is further. Or you see, vertically speaking, it's the upper curve. But I would prefer that generally as, I would refer to that generally as the further curve, the curve that's further away from the rotation center. Okay? And so the further curve is here, and that curve is currently expressed as y squared equals x. But now, as I have explained earlier, we need to express this as a function of x. We need to express that as a function of x, because right now we're at some random x value, at some instance of an x value. And so what is this value here as a function of x? And so now in that way, it's a quick math work right here. So y squared equals x. Okay, then we can take square root of both sides. Okay, take square root of both sides, and that gives me y equals a plus and minus square root of x. We always have to take the plus and minus square root. Okay, anytime that we're taking square roots and operation on both sides of our equation, of any equation. Okay, but now in this way right here, that means we have two expressions. So let's look at the curve itself again. This part of the curve that we drew right here, this part where it defines our enclosed area is the part where it's above the x-axis, or in other words, the y value has to be positive. The y value has to be positive. And so in that way, that led us to the decision that we need to express our curve here as y equals positive square root of x, because that will ensure we're landing into the positive y value. All right, and so now, so that means here's how I'm finding the cross section. The outer radius, or the larger radius, is that function's output when at this x value we're into that curve right here, that further curve. So now we have pi times the square root of x all squared. That's the area of the larger circle. Okay, so I'm going to make a note right here of the larger circle. Okay, and once again, the whole reason why we have to convert this, we have to re-express our curve as a function of x now, simply because we desire our final functional expression here to be having the variable that's consistent with this d expression. Okay, and now that's the outer circle. So the inner circle is from where the center of rotation, or from where we're looking at our axis of rotation, and that's reached to the closer curve, whichever the two curves here, whichever the closer one, that's the curve being the inner circle. That's the curve giving the inner circle. So the closer curve here in this case is that straight line. And I had that note right here, this straight line here is x equals 2y. So that means what? Again, we need to express that, see, that space right there. Okay, we need to express that as that height right here as a function of x right here, because simply at that particular x value, then how high does it reach? We notice that the height changes differently, right? When we at a different x value, we have a different height, different inner radius and different outer radius. Okay, and so in that way, now again, I am going to move out to my other board. All right, so x is given as in an equation x equals 2y. But that's a simple treatment right here. We just simply divide both sides by 2, and we're looking at the x over 2 equals y, or more friendly, more as a friendlier expression right here, an expression that's more friendly right here than y equals x over 2. So this is a function, or a 1/2 x. This is now a function of x. Okay, we have re-expressed our equation to express y variable as a function of x, which is consistent with what we need. And so in that case, now the area of the inner circle is supposedly an empty space when we're rotating it, but that counts too. Okay, so the inner circle is going to be having area pi times the radius that is regulated or determined by x over 2, but all square. So pi times little radius square. So larger circle and smaller circle. Okay. Larger circle and smaller circle, and in that rule I explained earlier, in just the way how the picture looks, then larger circle area subtract the smaller circle area. All right, so now we have that formulation. And as a little cleaner version, then now our cross-section area appears as following. Now, square operation here will cancel out with that square root, and that gives me pi x and minus pi times x squared over 4 right here. All right, so now I'm ready to complete that function to represent my cross-section area. This is my function in terms of x, as a function of x, to be consistent with this d expression right here. And this function now is the function that represents our cross-section area at any instance or at any x value given. Okay, and so now I'm going to fill it in. And of course, realizing that we have a common factor here, I can just keep that common factor pi in front of the function. And now I'm looking at x minus an x squared over 4. Okay, and so now we're almost done with our integral setup right here. So now one more step. Let's look for the start and the end of our accumulation. So I have explained that many times throughout my discussion lecture right there, my general discussion lecture, either with the disk method or with the volume method, because the two methods are essentially the same. But so now, since we're doing our rotation around the x-axis, and so in that way, consequently, each cross-section is being perpendicular, facing our eyes, of course, and perpendicular with the rotation axis there. Then in this case, the rotation axis being the horizontal axis, then our accumulation here is going to have to start on the left. That's the start. Start on the left and end at somewhere on the right-hand side. It starts on the left, okay, and it ends on the right. So now we're going to have to look at, hey, so now looking at this picture over here, the start seems like this end, the left end of this region right here before rotating. And then the right-hand side seems like, the ending seems like this, whatever x value here. So it is our responsibility to find out. Okay, so in this problem, the start and the end of the rotated region are not given as clearly as in those two examples I pointed out. I delivered back in the general discussion lecture, but there are clues for us to find out. Okay, so I pointed out in the picture over here. That's where the two curves are crossing each other. But now we have to do a little bit of math to find that. So now on my other board. So I have solved that y equals square root of x. That's one curve. And in the picture, this is the curve that's further away from the rotation axis. And then we have another curve being y equals x over 2. This is the curve where, at least within our region within our rotated region, then this curve is closer to the rotation center or the rotation axis. And so now in that way, to find the values of x, from the left to the right, reminded. Okay, so to find the values of x that's indicating where these two curves are crossed, as how I have explained earlier with the graph on the other board. Then now I'm going to just simply set the two expression in terms of x here equal each other, and then now we're going to solve for x. So now in this way here, I'm going to go ahead and multiply 2 to both sides, leaving me 2 square root of x equals x. And then now in the next step, I can go ahead and square both sides of my equation. That's a famous algebra step right there, to get rid of square root. Anytime that we're solving an equation that involves a square root right there, we can always square both sides right there. Okay, so left hand side becomes 4 times x, square root cancel with the square, and that equals x squared now. All right, and so in that way I can go ahead and subtract this 4x term to the other side, making it x squared minus 4x equals 0. So now I successfully turned myself into an equation to solve for x, but this is a quadratic equation. Okay, and so now with this quadratic equation, allow me to use the factoring method. You have your own choice for that. You have your own choice of method for that. You can also use the quadratic formula, or you can use the complete the square method. I just decide to use the factoring method, which looks a little more trivial to me. Okay, so here I can factor out x, and then factor the left hand side into x times x minus 4 equals 0. So now that quickly lands me into two solutions. I have one is x equals 0, and the other value is x equals 4. So that means our two curves here are crossing each other at these two x values. And so apparently this x value here, x equals 0, is lower, so it's on the left compared to the other x value being 4, which is higher to the right hand side. So now we have a clear picture, we have a clear, precise calculating. We have left end of our region right here is where the two curves cross. That has to be x equals 0 here, x equals 0. And the right end, okay, so this curve is the y squared minus x. And allow me to erase this so I can make space for a different notation right here. But this point right here is where it's x equals 4. Now we found it. So from the left to the right, we are starting our accumulation at 0, and we're ending our accumulation at 4. So I might seem to be going a little slow right here, but because I'm trying to present every single thought process, okay, every single step in my entire thought process right there. But so this is now the complete volume, the complete setup to calculate the volume. Okay, the complete integral setup to calculate our volume of this solid right there. Okay, so now on the next board, I'm going to spend some time erasing the board up, and we are going to complete out this this definite integral, and that will get us the final volume value right there. All right, so now with our complete integral being pi times x minus x squared over 4, and integrating from 0 to 4 here. The next step would be, well, I'm going to multiply that pi out front, but in the end this is simple enough, so I can combine two steps in one right there. I'm going to keep the pi constant coefficient here, and then I'm also going to find the antiderivative of this function right here. So we're looking at pi, and then in parentheses I have x squared over 2, but minus x cubed over 12, and fundamental theorem of calculus says I need to evaluate this antiderivative from 0 to 4 right here. Okay, so now at this point, it's another remark right here, but it is extremely highly recommended that you have to view this video lesson after you have learned what the fundamental theorem of calculus is, because you need to know what it is. You need to understand how this operates right here. So find my other video lesson about what the fundamental theorem of calculus is to understand how I do this. And so now fundamental theorem of calculus says that we're going to substitute for the upper limit of our integral into the antiderivative and do the same thing for the lower. But now I notice that, see here what I have is a 4r squared over 2 minus 4r cubed over 12. Okay, but now notice once we're substituting in that lower value here, it's a 0, and each term here is already in terms of x, so it's just one big 0 out right there. Needless to show all the little steps for that. Okay, but now at the final step right here, so we're looking at so this is a 16 over 2, that's making it 8, and then this is okay, so that's 8, and minus is 64 over 12, but that's cancels with 12, so it's 16 over 3 right here. All right, and so now final calculation here goes into 8 pi over 3. All right, and that's our final answer. Okay, that is our final answer. Okay, so now before I'm completely done with this problem right here, so one checkpoint right here for consistency right here. Final answer has to be a positive value, okay, because it makes no sense to be a negative volume, to have a negative volume. And then it's not going to be fun at all to have a zero volume. So this answer here makes perfect sense to always be a positive answer. So in any case, in any problem where you end up with a volume value, a volume answer being a negative value, go back and check your work. As well as anytime that you're ending up with a zero volume right there, go back and check your work somewhere. But then other than that, if you're questioning yourself about whether or not you have done all of these arithmetic here correctly, I cannot even guarantee to myself, to anyone viewing this video lesson, that I have done all little steps here correctly to arrive at that value here correctly. So forgive me on that as well. So when you are doing this on your own, make sure you double check or even triple check with all of your arithmetic work right there, your work substituting values in and all that. Okay. And so with this specific problem right here, I brought it up as an example to point out that there are cases out there where you find, yes, you have a given region as described here and being rotated around whatever the x-axis or the y-axis, but you have to be responsible on your own to find out the two ends. The left end, in this case, since it's going sideways, then the left end is the beginning of your accumulation, and the right end right here, where the crossing of the two regions, the crossing of the two curves that create the region, the right end here is the ending of our accumulation. But in the end, mainly for this problem, I want to illustrate that there are times out there where you have to find the two crossing points on your own right here. You have to find the starting and the ending of the accumulation on your own, and that just only takes a little bit of algebra. Okay.